Hello all and welcome to this video where we look at types of stationary points. Learning intention for today is to determine types of stationary points. That pretty straightforward. And then success criteria to help identify if we have been successful in our learning intention is whether we can determine the different, if we identify a stationary point, can we determine is a local minimum, local maximum, or a point of inflection? And then within a point of inflection, is it a positive or a negative point of inflection? So that's our goal. So let's have a look. Within stationary points, so within our stationary points, we have two main types. We have turning points, TP, and then we have points of inflections. Now within turning points, we have our local max, and then we have our local mins for turning points. And then within point of inflections, we could say we have a positive, and then we have a negative point of inflection. Now this terminology around positive and negative points of inflections is more just to help clarify. It's not common to describe a point of inflection as a positive or negative point of inflection. This is just more terminology to help us understand in class. While local min and local max, they're proper mathematics terminology or names. So if we go through and just looking graphically to identify types, if we had this graph below, it is quite clear that point A is a local maximum, m is equal to 0 at point A. At point B, again, m is equal to 0, and that is a local min. And then at point C, we have, just at that point right there, going through it, m is still equal to 0, and that is a point of inflection. Now, these tables that we have down here show us not only the gradient at each of these points, but almost more importantly, is the gradients around each of these points. What's the gradients to the left of this key point? What's the gradient to the right of the key point? And if we notice at a local maximum, we have a positive gradient on the left, it is going up. And then on the right, we have a negative gradient. Okay? So that's what this is showing. To the left of a local maximum, we have a positive gradient. To the left, at the point, of course, the gradient is 0, and then to the right, the gradient is negative. Now, if we look at a local minimum, okay, the gradient is going down, so the gradient is negative to the left, and then to the right, the gradient is positive. And again, that's what that is showing here. To the left, it's negative. To the right, it is positive. Hopefully, you're already maybe starting to think and realize this is really key information. And there's a difference here. It is quite clearly there's a difference here between the local min and the local maximum. The maximum, it's positive to the left, while for the minimum, it's negative to the left. So since there's a difference in the traits, we can use that to identify the type. But then that raises the question, what about a point of inflection? Well, point of inflection, the gradient in this case is going positive. It goes to m equals 0, but then again, directly afterwards, it is positive. So we can quickly identify a point of inflection. In this case, I'm calling this a positive one, a positive point of inflection, because to the left is positive and to the right is positive, is that the gradient is the same on both sides, either to the left or to the right. In this case, it's positive. And then for a negative one, so just quickly doing a little rough sketch, if we had something like that and we had a point of inflection right there, to the left is negative, to the right is negative. That would be what we're nicknaming a negative point of inflection, because to the left and to the right of it is negative. The gradient is negative. So this is how we can identify. If for a maximum, it's a gradient to the left of it's going to be positive. For a minimum, the gradient to the left of it is going to be negative. But for point of inflections, the gradient is the same on both sides. So once we find that out, then we can determine the type of stationary point. So let's do an example. For the function f, where the domain is all real numbers, the codomain is all real numbers, f of x is equal to x cubed minus 5x squared plus 3x plus 1. Find the stationary points and state their nature. So first off, we need to find the stationary points. Well, how do we find the stationary points? We need to, as always, we need to find the derivative. And then step 2, we need to let, let's just, this is f, so it would be f dash of x equal to 0, because the stationary points occur when the gradient is equal to 0. So let's do that. It follows on, looking at f of x, it follows on that f dash of x is equal to, and using our differentiation shortcut, multiply by the power and take 1 from the power, 3x squared minus 5 times the 2 is 10x, 2 take away 1 gives me, or just x to the power 1, 3x, that's the same as 3x to the power 1, so 3 times 1 is just 3, take what away from the x to the power 1 gives us 0, so it's just 3, and then the 1 disappears. So there's our derivative. F of x is equal to 3x squared minus 10x plus 3. We are going to now let f dash of x equal to 0. It follows on that 0 is equal to 3x squared minus 10x plus 3. Ooh, nasty, nasty, nasty. Why is it nasty? Well, it's got x squared terms, got a coefficient. That means we can't use basic inspection. We could try and use the cross method to try and factorize this and solve for x. Otherwise, we might need to use the quadratic formula or complete the square. But to complete the square, we need to take out 3 as a common factor as well, which isn't nice having the 10. So let's try the cross method. Put our cross in here. Right, we're going to need 3x and x. That's the only way we can make x squared. To get 3 is 3 and 1. So we want 3 and 1. Get positive. We need a negative 10. So let's make both of these negative. So negative 1 times x is negative x. 3x times negative 3 is negative 3x. Negative 9x, my apologies. Negative x minus 9x, that gives us negative 10x, and that works lovely. That gave us the middle term. So it is clear from here, from that, 0 is equal to now 3x minus 1, x minus 3. So from the null factor law, using null factor law, it follows that 0 is equal to 3x minus 1, or 0 is equal to x minus 3. Therefore, x is equal to 1/3, or x is equal to 3. So we've now found the x coordinates of our stationary points. We know one is that x is equal to 1/3 and x is equal to 3. To point out here, it's not saying find the coordinates of the stationary points. So the question isn't very clear, but we would want to, because it's a point and it's using the word point, it's not saying find the x coordinates of the stationary points, it's saying find the stationary point. Point implies a point on the Cartesian plane. So we're going to want to find the y values so that we know the actual coordinates of these. So let's do that. Okay. So we're going to let x equal to 1/3, and we're also going to let x equal to 3. So it follows on f of 1/3 is equal to 1/3 cubed minus 5 1/3 squared plus 3 by 1/3 plus 1. That is going to give us that's 1/9 minus, no, that's 1/20. 3 times 3 is 9, times 3 is 27. We will make mistakes, it's alright, we learn from them. That's going to be 1/9, so that's going to be 5/9 plus 1 plus 1. So from that we get, we're going to have to make these all over 27, so times by 3 for the 5 over 9. So we get 1 over 27, take away 15 over 27 plus 27 on 27 plus 27 on 27. That gives us 1, take away, that's going to be minus 14. 27 times 2, 20, 40, 54, take away 14 is 40, so we get 40 on 27. And then for the other one, we get f of 3 is equal to 3 all cubed minus 5 times 3 squared plus 3 by 3 plus 1. We get 27, take away 3 squared is 9 times 5 is 45 plus 9 plus 1. So 10, take away the 45 is negative 35. Let's start the other way. 27 plus 10 is 37. Take away 45 is 37. Take away 45. Sorry, doing this late at night, so mental maths isn't with me. Get my brain to work. It is 8. Negative 8. Oh my god. Negative 8. So our two stationary points in coordinate form are 1/3, 40 on 27, and the other one is 3, negative 8. I'm going to make myself a little bit of space here. Rightio, we need to now determine the types and state their nature. Now, if you realized that x cubed minus 5x squared, that is a cubic function, and it's a positive cubic function because the x cubed term is positive, then we know this function is either going to look like that, or it is going to look like that. Okay, we're either going to have m equals 0 once, or we're going to have m equals 0 twice for a cubic function. Which one is it? Well, it's clearly the one on the left because we've got two different coordinates. We've got two different stationary points, therefore it must be the one on the left, so it's not this one. So looking at this, we could go, well, it's a positive cubic function. It needs to be trending upwards, so the left stationary point must be a local max, and the furthest left one is 1/3, 40 over 27, and the furthest right must be a local minimum, which is the 3, negative 8. So if you knew the function and recognized its form, then that's the shortcut. But what if we don't recognize the form? Well, we need to check what the gradient is to the left and to the right. So I would suggest picking numbers that are easy to calculate with. There's no point going, oh, to the left of 1/3, let's maybe do 1/6. It would be silly to do f dash of 1/6. While it is to the left of 1/3, it's just not making your life easy. Pick easy numbers. Pick 0, pick 1, all of those sort of ones. So let's do f dash of 0. We want to find the gradient to the left of 1/3. So f dash of 0, our function for, where did I find f dash? Here we go. We're going to be using this. That was our f dash. So we get 3 by 0 squared minus 10 by 0 plus 3. So we get is equal to 3. So that is a positive gradient. So to the left of 1/3 it's positive. Now we need to check to the right of it. So f dash of, and again we're going to pick a number to the right of 1/3 because we're dealing with this one, dealing with this coordinate point at the moment. So to the right of it, well, to the right of 1/3 would be just 1. 1's a nice easy number to pick, so we get 3 by 1 squared minus 10 by 1 plus 3. So we get 1 squared is 1, times by 3 is 3, minus 10 plus 3, so we get negative 4. So the key thing, that first one it was positive, for this one is negative. So we have, quickly, we have a positive gradient, then a 0 gradient, then a negative gradient. So up, 0, down. That must mean, well, this one is a local max. So if you didn't recognize the form, that's how you'd find it. Check the gradient to the left, check the gradient to the right, and then compare with these tables. In this case, we had positive to the left, then 0, then negative to the right. So it clearly needs to be a local maximum, which matched with recognition up the top there. This then begs the question, what about the second turning point at 3, negative 8? Well, we need to check the gradient to the left. Now, we've already actually done that, because to the left of 3 and before, and it needs to be somewhere between the stationary points, like you can't have it all the way to the left of the second one as well, but we found f dash of 1. Now that's in between these two, between 1/3 and 3, so we can consider this as our to the left. So to the left we know that it is negative, and then we want to check to the right, so we need to just be right of 3, so I'm just going to do f dash of 4. Keep the numbers as small as possible. We get 3 by 4 squared minus 10 by 4 plus 3, so we get 3 by 16 minus 40 plus 3. 3 times 16, 30. 3 times the 6 is 18, so 48. Take away the 40 is 8, plus the 3 is equal to 11. And it turns out that that is positive to the right. I'm just going to neaten up some things here to the left when considering our second coordinate, but it was to the right. This was to the left of the first coordinate. So for that second coordinate, to the left of it, the gradient was negative. That must mean it's coming down. It then goes gradient of 0, and then to the right of it, it was positive. Negative, 0, positive. That must mean it is a local min, which matched our recognition. But clearly, if you recognize the function, that is much quicker than finding the derivative at 3 different points. But if you didn't recognize it, or some polynomial that you weren't used to, or even not a polynomial, we can still use this strategy when it's not a polynomial. We could use it for trigonomic functions. We could use it for any type of function. Check the gradient to the left of the stationary point. Check the gradient to the right of the stationary point. That'll tell you what type of stationary point it is. Sketch the graph labeling all the key points. Oh, wow. Right here. So we had a TP turning points at 1/3, 40 on 27. We had another one at 3, negative 8. 3, negative 8. Okay, let's put our axes in like that. Okay. 40 on 27 is less than 2. Less than 2. So if we say each one of these blocks is 2, so 2, 4, 6, 8, negative 2, negative 4, negative 6, negative 8. And we'll do 1, 2, 3, 4, 5, 6. That gives us what should hopefully be enough. So we know we have a turning point at 1/3, 40 over 27. So 1/3. So we have one turning point there. Let's not use black, let's use a different color. We have one turning point there, and we have another one at 3, negative 8, which is down there. So I can put in my little curve through that. I can put in my little curve through that. But to sketch the rest of it, we have to go back to our normal sketching strategies. We need to have our intercept because we're asked for all our key points. So for our y-int, let's let x equal to 0. So it follows on, y is equal to, and our original function was x cubed minus 5x squared, x cubed minus 5x squared, plus 3x plus 1, plus 3x plus 1. So we get 0 cubed minus 5 by 0 squared, plus 3 by 0 plus 1. So of course it's the constant term as always. So y is equal to 1. So we can add that in. We got a key point there. So that was 0, 1 there. That key point is 1/3. 40 over 27. Down here we have 3, -8. Now we need to find our x-intercepts. So x-intercept, we of course let y equal to 0. So we get 0 is equal to x cubed minus 5x squared plus 3x plus 1. Rightio, rightio. So how are we going to go about this? We know from the factor theorem that if f of some variable a turns out to be equal to 0, so just a reminder, it follows that a is a factor. So we could do some trial and error to try some numbers, and we also know that there needs to be an intercept between 1/3 and also 3, and I'm leaning towards hopefully betting that it's at +1, because the line has to come down, it has to go from the local max down to the local min. So let's try quickly what f of, that was y is equal to, so let's see what y of 1 is equal to. We get 1 cubed minus 5 by 1 squared plus 3 by 1 plus 1. So we get 1 minus 5 plus 3 plus 1 is equal to 0. So we can say quite clearly that using the factor theorem, x minus 1 is a factor. So hopefully you remember that. Bringing back maybe good memories, maybe painful memories, but like I've always said, once we finish a topic, that is becoming assumed knowledge now for future topics. We're in year 11 mathematical methods. Nothing is, we aren't, the topics aren't discrete anymore. It's not, oh, we're going to do a bit of this, then there's a bit of this, and then there's a bit of this, and there's no connection between them. There's complete connection between all our topics. So if you're not all over the factor theorem or the null factor law or factorizing cubics, then you got a bit of revision to do. So we get 0 is equal to x minus 1 bracket. It is quite clear that we need an x squared because x times x squared gives me my x cubed. The constant at the end, well, I need -1 times whatever the constant at the end is here. So -1 times by question mark has to give me my +1. So that has to be -1 there. And then we're left with whatever our middle term is. So our middle term, let's call it b. We know b times x, and then we also do, it's going to be bx, sorry. So we go bx times by -1, and then also, because I'm looking at how will this 3x term be built. That 3x term will be built by bx times by -1, and then also this x times -1 also gives me a term with an x in it. So we get plus x times by -1 must all come together to give me 3x. So this is a shortcut way of doing equating coefficients. This is more a mental arithmetic way of doing equating coefficients, but you could do equating coefficients. You could have done long division. Any of those methods would work for doing the full factorization of it. I'm just doing it a bit of a shorter way. So it follows that we get negative bx minus x must equal to 3x. So we get negative bx is equal to 4x. So b is equal to negative 4. So we can put that in there, or I'll write it off to the side. We get 0 is equal to x minus 1 bracket x squared minus 4x minus 1. Let's make sure I've done that properly. Because this is looking like, and let's also double check that that gives me my, so give me 20 seconds. I'm just going to do some mental arithmetic in my head to make sure I have done the correct answer here. 1 times x. Yeah, so that is correct. But how do we factorize x squared minus 4x minus 1 to get the other factors? Because we need the other factors to know the other intercepts. We're going to have to complete the square for that x squared minus 4x minus 1. So this question is drawing on a lot, and I mean a lot, of prior skills and knowledge. So we could write this as 0 is equal to x minus 1 bracket x squared minus 4x. So we look at our middle term, our negative 4x. We halve it and then square it. So 4 divided by 2 is 2. 2 squared is 4, so we write plus 4 minus 1. So 0 is equal to x minus 1, x minus 2 all squared minus 5. And then we can write this x minus 1 all bracket x minus 2 all squared minus the square root of 5 all squared. So we've made it into a difference of perfect squares. So we finally get 0 is equal to x minus 1 bracket x minus 2 minus root 5 bracket x minus 2 plus root 5. So that's a lot of work. So what do we get from that? Therefore, x is equal to 1. It is equal to 2 plus root 5. And it's also equal to 2 minus root 5. So that gives us our final intercept. So let's put those in. We have one there, which is 1, 0. Now we have to estimate some sizes here. Roughly, what is the square root of 5? Well, 5 is between 4 and 9. The square root of 4 is 2. Square root of 9 is 3. It's between those two, so it's 2 point something. So we've got 2 plus 2 point something. So it's going to be 4 point something. So we can put a mark in there. Close enough is good enough in this sort of form. So we get 2 plus root 5, 0. And our last one, 2 take away 2 point something, is going to be negative 0 point something, which makes sense with our graph. It's going to be roughly in there. So we've got 2 minus root 5, 0. We have all our key points finally. So we can sketch our graph. Goes down like that, continues on, because our original domain is all real numbers, so it's not restricted in any way, shape or form. Comes up, goes down, goes to there, and I apologize for that terrible line. Down to there, up through there, and continues on and on. So wow, that had a lot of work in it. So the only new part to that The only new part was finding the derivative defined where it was all on the previous slide. All of this was the new bit. We found the derivative, found where the stationary points are by letting the derivative equal to 0, and then we checked to the left and right of the derivative to make sure we knew what type of stationary point it was. All of this slide is all prior content. Finding y-intercept of a cubic, finding x-intercepts of a cubic, so having to factorize a cubic, so either by long division, using the null factor law, by equating coefficients, and then once we did that, when we got it to x minus 1 and then x squared minus 4x minus 1, we realized, well, for that quadratic of the x squared minus 4x minus 1, this bit here, well, the only way to factorize that was to by complete the square. So we had to go back to right at the start of the year, add in completing square for just that little bit, and that allowed us to fully factorize in the end and get our intercepts. Now, the scary thing is, I guarantee you there's going to be a question like this on the test, because it tests your prior knowledge, it tests you applying your prior knowledge, it tests you relating that prior knowledge to a new topic, it tests your use of derivatives, it tests your use of derivatives to check this type of turning point. So in one question, I get to check 5 of your skills, 5 levels of understanding, 5 bits of knowledge. So we love this type of question as a teacher because we get to check all those things just in one question. So if you're not all over what we did, go back, review the video. You can send me an email. You can get my email on Compass or use Google Classroom or Edmodo. But either way, you can contact me about this if you need more help. But that's that. Now, that was doing it by pen and paper. What about doing it by CAS? So using your CAS, state the values of the x-intercepts, the roots, y-intercepts, state the gradient when x equals 1, and the coordinates of the local minimum maximum for the following. Rightio. Okay, so we're going to do this all with CAS. The only thing I'm going to write down is what the notation we used in the CAS and the answer. That's all I'm going to do. So first off, like I always say, because we're going to be doing lots of things with this function, let's define it. So we're going to define, in this case we'll define as f of x is equal to x cubed plus 13x squared minus 10. So let's jump over to our CAS and start with that. So I need to open up the CAS. There we go. So let's, need to have it selected. So define, or for those that forgot how to do it, menu 1, define f of x is equal to x cubed plus 13x squared minus 10. X cubed plus 13x squared minus 10. Did I get that right? Yes. Okay. Done. Now the next thing we want to do, because we're going to be doing a bunch of work for the derivative, we need to define the derivative. We want to define it. So we're going to define, and we're going to go g of x is equal to, and now we're going to go menu, calculus, because this is part of this, the derivative, and we're differentiating with respect to x, of, we're going to just do the derivative of fx. Done. So we've got the original function stored of f of x, and we've got the derivative stored of g of x. So we can now use those two over and over and over again to solve all the questions asked in the PowerPoint. So in the PowerPoint, state the values of the x-intercepts. So first off, x-intercepts, that's related to the original function. We want to go menu, algebra, solve, and we want to solve f of x equal to 0. We're making y equal to 0, and we're solving for x. And there is our 3 intercepts. So I'm just going to write to 2 decimal places just so I can remember easier. Negative 12.94, so we get So what we did was solve f of x equal to 0, and we got x is equal to negative 12.94, negative 0.91, negative 0.91, and 0.84, no, 85, 0.85. So that's x-intercepts. We need to find our y-intercept. So we're going to solve f of 0, or actually we just can do f of 0. That's our next command. So each one of these is command solve this one, and we're just going to do f of 0. We're going to let x equal to 0 to find our y-intercept, and it follows on y is equal to, so f of 0 gives us negative 10. Negative 10. State the gradient when x equals 1. So just as a reminder, and I haven't written it in, but for the derivative, this was a key thing. We have define g of x as equal to the derivative of f of x. So we had to put that in there, and then to get our next bit of information, we're going to find the gradient when x equals 1. So we're just going to go g of 1. That'll tell me the gradient at x equals 1. So g of 1 is 29. So the gradient is equal to 29. And the coordinates of the local minimum and maximum. Okay, so the local min and max, they're going to be when the gradient is equal to 0. So we're going to solve the gradient g of x equal to 0. So menu, action, no, algebra, solve. We're going to solve g of x equal to 0. And what do we want to find out? We want to find the x. So we get negative 26 on 3, or x equals to 0. So we got from this, x is equal to negative 26 on 3, and x is equal to 0. But it's asking for the coordinates, so we need to find the y values at that point. So we're just going to go f of negative 26 on 3, and we're also going to go f of 0, which we actually already know. We've done that already. That was equal to negative 10 up here. So it turns out our y-intercept is also one of our turning points. So f of negative 26 on 3. F of negative 26 divided by 3 is 8,518 on 27. 8,518 on 27. So our two turning points end up being negative 26 on 3, 8518 on 27. And being a calculator one, it's not asking for it in exact values, it just says state the values, so you could do these as decimal estimates for that first turning point, and then the other one is at 0, negative 10. It's a positive cubic, so the one to the left, that'll be local max. So this one is the max, and this one is the min, local min. It's the exact same process for this second question. So I'm going to leave that one because it's almost a 40-minute video already. I'm going to leave that one for you to do and to try. And that is it for finding the types of stationary points. So to review, the only new bit in all of this was to determine the type of stationary point. You just need to look at the gradient to the left of it and the gradient to the right of it. And then once you know those two, you can determine the type of the stationary point. If you're doing a question like this, which is a cubic, find the stationary points, and then having to graph it, there is heaps of work. That's a grind. You've just got to knuckle down and go, okay, I'm going to have 5 to 10 minutes worth of work just in this problem, grinding it out. That first slide, part A, that's all the new bit. Using the derivative, find the stationary point, find the type of stationary point. Second bit, that's finding all the other key points. We've done all of that sort of stuff before. Doing it on a CAS is clearly much quicker. So to reflect, learning intention. Determine types of stationary points. We've shown how to, and you can check by gauging against your success criteria. Do you know the difference between a local min, a local max, and a point of inflection? And that is right there on that slide. Like I've said, if you have any questions, hit me up via the school email. Thank you very much, and that's it for tonight.